things like the line integral of f1 dot t, and again with respect to arc length, right? That was one of the ones I asked you guys to compute. And then we're going to go ahead and have you guys do this one also. And I said what I would, oh no, f2 dot t. So I think I'm going to do this one, f1 dot t, and then let you do that one. And then for the other ones, I think I'll do f2, okay? So the other exercises are, we want to compute after this the line integral f1 dot n ds, where these are, okay? So these are vector fields. And we can compute a line integral if we have a parameterization of the curve, right? So we do, hopefully, right? When you see this curve, you see that I'm describing C. And you guys, I saw you sketching the vector field for F1, and I saw some really cool things. But when I'm talking about the unit circle, I guess I'm picturing rotating around like this, right? And so at any particular point on the unit circle, so here's the point 1, 0, for instance, right? I can picture F1 vector as also going 1, 0. Or here at 0, 1, right, it would point straight upward. Or here at, let's see, what would this be? Sure. I was going to do 1/2 radical 3 over 2, but yeah, we have all those nice points we memorized. You can see that the vector field, right, is really kind of an outward motion, right? Bless you. Matter of fact, this is a classic example. You might call this a radial vector field, right? Because everything's being pushed out from the center. If these are forces, let's say, and we're talking about work done, we're imagining anti-gravity, right? Instead of pulling in, we're pushing out. And the farther you are away, the stronger it gets. That's the total opposite of gravity, right? Okay. So I guess the question is, what does this equal? This f1 dot t ds, okay? And so in order to compute this, in order to compute t, I'm going to use the fact that in general t is equal to what? Well, the unit tangent vector. Yeah, I remember this r prime of t over the magnitude of r prime of t. I remember this formula, right? But that assumes I have some r of t already, right? But if I'm talking about the unit circle, right, of course there's a natural way to get a parameterization of the unit circle. At least it's natural for you guys because you've done so much calculus and trig. Automatically you want to think, well, okay, r of t is going to be, let's say, cosine t sine t. How's that look? Okay? By the way, that will work if I let t range from where to where? Well, let's say 0 to 2 pi, right? So that'll be my r of t. And if I'm going to use this formula, r prime of t, I guess I'll need r prime of t is going to be, well, it'll be negative sine of t cosine t. Yeah. And as far as the magnitude of r prime of t, how do you get that? Well, you're going to square root the coordinates squared. But what are you squaring? Well, you're squaring the sine of t, forget the negative, it's gone, and you're squaring the cosine of t. Oh, okay, so what's the r prime of t going to equal? That's going to equal 1 in my example, right? So that's kind of nice. When I say I'm going to compute this line integral, what I'm about to do is I'm going to say that this equals, and I'll make a change. And instead of writing a ds integral, I'm going to write a dt integral. Because now I have a parameterization besides arc length. The parameterization I'm using is up here, okay? And so, and here too, right? My limits of integration are going to be from 0 to 2 pi. This okay? And now f1, of course, well, that's my xy dot. And then what we're dotting it with, I guess, is just r prime, because the unit vector there was this. So we have negative sine t cosine t. Although I guess the issue is I wrote xy again. Yeah? And I kind of don't want that. Because I want it to be in terms of t. So we need to fix this. But we can, because where are we? We're talking about being on the unit circle. So really, what is x and y if I'm on the unit circle? Cosine t and sine t, right? So we'll fix this by using the fact that x is cosine t and y is sine t. Make sense? So, okay, let's see what we get. We're going to do the integral from 0 to 2 pi of, well, this would be cosine t comma sine t dot negative sine t cosine t so what are we getting? Let's see. We get negative sine t cosine t plus sine t cosine t. What's that equal? 0. So we're integrating 0 dt. Right? So we get 0. Okay.
Which tells us what? What does that mean? Like, what is 0?
0 work done, because we've gone around a circular path.
There's 0 work done. That's absolutely right.
But didn't you do a lot of work to get there? See, this is what
I certainly did. I certainly did.
Is it because the positive and negative?
I have negative order. Every work in my life is positive.
So should we do this one? Should we do this one, F2?
This is where I fell apart from life.
We should do this one. All right, so here we go. F2, what's going on here? What's going on here? You guys sketched the graph for me, and it looks very similar. I mean, one thing that's different, even though the orientation of the circle's the same, right? One thing that's different when we did F2, yeah, you guys have different looking vectors, right? So the vectors for F2, now I'm talking, I'll draw those in green, right? Negative y comma x. So when I'm at 1, 0, where am I pointed? Let's see. This is the point 1, 0. So I'm at 0, 1, right? So this one's pointed up.
That just follows the circle.
Well, let's check that. Yeah, this one being at 0, 1 is going to be pointed which way? Negative 1, 0. I agree with Aaron here. It seems like it's following the circle, right? Okay? So here we have kind of a flow going on, right? This is like exactly the unit tangents that you want. You can see after some work that this is like the ideal way to get to compute the work done off of this force, right? And so what changes? Well, not much, I guess. I mean, when we do our integral, it's still going to be from 0 to 2 pi. The biggest difference, of course, is that, and we still do the same parameterization, the biggest difference is that what are we dotting with negative sign and cosine? I guess we're dotting, oh, it would be negative sign and cosine, right? So we're going to dot this vector with itself. Question? Hold on, I skipped steps. Am I going too fast? So what do we get?
1.
Yeah, because you get sine squared plus cosine squared, right? So we're going to integrate from 0 to 2 pi 1 dt, right? And so what do you get?
2 pi.
Right, because you get t, and so you get 2 pi. Okay? If we were to compute this, f1 dot n, now here's a question. Do you know what the normal vector looks like when you have one of these things? Well, the normal vector, of course, I guess the big thing to understand is that it's perpendicular to the tangent vector, right? And so, yeah, it's kind of a negative y comma x, right? So it's interesting because the normal vectors line up perfectly in this situation. And so it's time to go to your book. That's where it's time to go to. Because these are, again, my degree is from CASE, right? I told you about that acronym. You didn't know CASE was an acronym? Copy and steal everything, yes. So if I go back to section 2 for a minute, I have sections 3 and 4 up here. We worked on 3 last time, we worked on 4. Go ahead, Aaron. While this is coming up, go
I
ahead.
just wanted to know, how does it make sense for it to take 2 pi of work? Wouldn't it make sense for it to take like negative infinity of work? Because it's just kind of getting pushed along.
So I guess as I go once around, work is force times distance, right? The force is moving me that far. What's the circumference of that circle?
4 pi? Or
Circumference.
2 pi.
2 pi r. So it seems like arc length, the numbers kind of match kind of nice. But just so you know what it was we were computing, there's a section we didn't really talk about when we talked about line integrals. And it's this: circulation and flux. Here's your words: circulation and flux. You physics people, have you talked about flux?
Yeah.
You movie fans, have you talked about the flux capacitor? My niece and nephew love Back to the Future. Anyways, what we just computed was the circulation, okay? The circulation of a vector field on a curve is given by the formula we just computed. And sure enough, yeah, I stole example 7 big time, right? There's your work. I said, wow, would that be a nice, what if this were a quiz? Well, we get 0 and we get 2 pi, right? So again, these are the radial field, and the other one, they call it a rotation field. I like that name, okay? And again, it sure is nice to have the book, which can do much better sketches than we can, right? Yeah, there's your rotation field. Okay, this is kind of nice. But even the other example, that's example 9. Right, not 8, let's look at 9. Flux. F dot n is flux. And so if we look at the solution to example 9, I think at this point you'll see why I decided it wasn't worth working out. See that? You get 2 pi for the radial this time, because now the forces are going the correct way. There's no projection at all. And you get 0 for the flux of the rotational vector. Do you see what I'm saying? If you think about it, flux is orthogonal, let's say, or perpendicular to the circulation, or the flow, you might say. Okay? So this is, by the way, everything I just did is two-dimensional. Where they really want us to go with this is three-dimensional. But before we go there, I feel like it's really important to, hey, let's understand this really well. And that's where I said, I'm going to spend 30 minutes today on this. I thought you'd spend 30 minutes, and it got to the point where I said, no, I'm going to work some of it out. Any questions so far? So again, flux is the dot product with N. Circulation is the dot product with T, right? But by the way, in both cases, we had something important. We had something called a simple closed curve. And that's one of our vocab words for today. I'm about to write down in a little bit. Hey, we skipped an example, and I think it's worth showing, at least the picture, and probably the solution. Check this out. See that one? Circulation of a three-dimensional flow. A tilted ellipse, right? What do the unit tangent vectors look like? Yeah, see, this is 3D. Is this something you can see? I think that's cool. It's an ellipse, but this particular vector field depends on 3 dimensions, z, x, negative y, so the red arrows seem to be pointing all over the place. You guys with me? But remember that dot products are related to projections, and that's why the next thing they say is, let's look at how the force is projected onto C. And we did show you this kind of thing last time. Okay? And maybe one more thing to look at, when they do the computation and you have this closed curve, hey look, 2 pi comes back. Interesting. And then they're going to talk flux. All right, I'm going to move on from section 2. We're beyond that, but I said I want to start with those ideas to get into what we're working on now. We've been working on line integrals. But you'll notice there's one section we didn't cover from section 3, line integrals on closed curves, right? See this symbol, guys? That symbol there comes back. What does this little circle mean? That's going to mean that, hey, my path I'm taking is a simple closed curve. And that comes up so often that we have its own little symbol for it. Last time we were here, we learned something called the fundamental theorem of line integrals. And it had to do with if you had what was called a conservative vector field. So now I'm really testing our vocabulary, right? What the heck did conservative mean? Not liberal? No. Conservative meant, when I say F is conservative, do you remember what it meant? It meant that something exists. Oh yeah?
It's the gradient of a potential.
Yes. F is the gradient of, we called it phi, right? And this was called a potential function. And part of what we did last time was we showed you guys how to find a potential function. And the other thing we did was we mentioned that there's a test to see if F is conservative. Do you remember what the test was? There were partial derivatives involved. You guys remember that? All right. We didn't show why it works. We just mentioned that it works. And we couldn't really say why. By the end of today's class, I should be able to show you why the test for being conservative works. But conservative meant that there is a potential function, but it also meant one more thing, which is an important idea, and that meant that the integral, the line integral, can be computed and here's the phrase we used last time, independent, yes, of path. Independent of path, right? And so the one section that, and so these are all ideas from section 3, right? 16.3. In a nutshell, this is really what we had last time. But if the line integral is independent of path, and if you have a simple closed curve, what would have to happen? Well, it's something that we saw happen in our example. The line integral will end up equaling 0. Now, why is that? One explanation is given here in the book, and I thought I'd show you. I thought it was cool. Oh, we signed out of that text, but that's not the one we need. Here we go. Line integrals on closed curves. Oh, well, actually, here's one reason. Remember phi of b minus phi of a? All that matters is the endpoints? Well, if you're starting and ending the same place, phi of a minus phi of a is 0. There's one explanation. Another explanation, which is really kind of cool, is given here. You see that C? That's a circulation, right? We're going to go up C1, we're going to come back on C2. But when you come back on C2, if you say, hey, we could have come back on C1. So go up C1 and come back C1. Well, those are going to be opposites. Whatever you got for your work, you could think of it as negative work when you go backwards. Okay? You're fighting the force instead of gaining from the force. And so yeah, that's this idea that simple closed curves in a conservative vector field, we're going to have, because of independence of path, we're going to have 0 for the integral. And you guys saw an example of that today without, knowing all the vocab yet, I guess. So, what is my job today? My job today is to present what's called Green's theorem. This is really kind of cool. This will be another way to compute line integrals. What it's going to say is the line integral equals a double integral. Now, wait a minute. If you want to have a line integral, how do you know it's a line integral? Because what will I write? A C. And so you'll have a curve in mind, right? And let's just stick to 2 dimensions for now. A curve. And so I'll also have maybe a ds, and maybe I'll have who knows what in here. We've actually seen different ways of writing the integrand already. And I'm going to show you another one. That's too bad I closed section 2, because that's the first place they show it, and I meant to show it. So I think I'll go back to that in a moment. The double integral. How do you know that you have a double integral? Well, there's 2 of those, but what else? What am I going to write down here?
R.
I'm going to write an R. And I'm also going to write what? dA for area, right? By the way, if I put a number 1 here, what am I actually doing? What am I computing if I put a 1 here? The area of
The line.
R, right?
Yeah.
You actually get the area of R that way, whatever R is. Well, here's what's really kind of cool in my mind. These are equal, and here's the deal. If you have a simple closed curve, which is what that symbol means, then I'm picturing, here's my C. Right? Well, guess what, guys? Here's your R. It's that region. And it's really beautiful that somehow the value of this line integral is the same as the value of that area, right? That double integral under the right conditions, okay? And that's what we have to get at today. Now, in terms of the examples we were just showing you, we had, let's see. Oh, yeah. This. We had f1.t, and then we had f1.n. I want to think about f1.n for a moment. When I say I'm computing flux, so let's talk about two-dimensional flux for a moment. What is that? So 2D flux, we can write as a line integral over C, right? And let me put the little round symbol to say it's a simple closed curve. I'll do that usually when I talk about flux. And do you remember what I said I was going to put here? ds, but do you remember what it was we had here for flux?
It was
F dot n, yes, F dot n. Now, F is a vector field, right? N, on the other hand, see, when I ended up using the parameterization, right? N ended up being, let's see, it was negative y comma x, right? And then F was my, whatever it is, x comma y. Nah, I don't want to write that. I want to write, well, I think I want to show you, so hang on one second. Okay, so again, when I did my F, okay, if we're in two dimensions, I could say that my vector field F is the vector F and G, where F is a function of t. You know, what hopefully happens is that I can write F as a function of t and G as a function of t. Because what we want to do in order to compute this thing is we're going to write dt, and we're going to say that the flux is the integral from A to B, where you have some parameterization, right? Now that only works if we take the curve C and parameterize it by, I don't know, let's say R of t, right? R of t. So if you have that, then the flux equals integral from A to B. I guess for shorthand I'll write F comma G, even though I know it's F of t, G of t. What am I dotting it with? Well, you saw what we dotted it with for the circulation, right? For the circulation, what was the unit tangent vector again? Do you remember? The unit tangent vector again. We did r prime of t over the magnitude of r prime of t, right? Oh, but wait a minute. R prime of t is not right for us because we're doing the normal vector. To get the normal vector, I have to switch x and y, and I have to add a negative sign, right? Because it's negative reciprocal slope. And then the other thing that's interesting is ds means unit speed, and so you get this r prime of s right here. And so what happens is the r prime of t absolute values are going to cancel. What goes here? Well, instead of putting, so let's see, if r is given by the vector x, y, bless you, then I could say that to get n, I want negative y comma x. And so I'll throw this in here, negative y of t, comma x of t. Gee, is that ugly? Well, but let's write it down. I guess flux can be written a to b. If we dot these, let's see, we get negative f of t. I'm sorry, these are primes. Because we had r prime of t, right? We're taking the r prime of t is the tangent, so these are the reciprocal of the tangent. So we get negative f of t, y prime of t, plus, can you give me the rest? If you can give me the rest after all that chicken scratch, then I'll say, wow, we learned something. G of t, x prime of t? Really? How many are with me, kind of? Yeah? dt? I'm impressed. If that makes sense, that's really cool. And then what you do is this. You say, well, notation. What do we know about x prime of t? What does that mean? That's the Newton way of saying it. What's the Leibniz way of saying it? dx dt. And so, if I have x prime of t dt, the differential way of writing it is just call that dx, right? You've seen that before in Calc 1. You've seen differentials here in Calc 3. And so I guess my point of this little chicken scratch explanation is that you will see the flux integral written this way. You will see it computed this way. But you will also see the following. Integral, back to the line integral form, and you'll see people write this. Little f, and see where it says y prime dt, I can write dy. So maybe negative f dy here, plus g dx. And that's kind of a nice, concise way of writing flux. Negative f dy plus g dx. Okay? So, the job today is to explain what Green's theorem is. I want to state it, and then we'll take our break, and that's where we're at. Okay? So here goes the statement. Question first, Matthew?
No, never mind.
Never mind? Okay. So here's Green's theorem. Let C be a positively oriented piecewise smooth curve that bounds the region R in the plane. Okay. If f of xy and g of xy are, if I write this, do you know what I mean by my abbreviation here? Continuously differentiable on R, then here's the formula. What's that say? Okay, that's a line integral, right? And what it's going to be here is, and this should make sense to you, f dx plus g dy. So again,
Wait, is it FDX, not negative FDX?
it's f dx, yeah. This is that new notation. Actually, when you looked at the flux, I had negative f dy, you'll notice, because it was a y prime that kind of showed up there. Anyways, what this equals is a double integral over R. Double integral of what? I'll put it in parentheses, dA. What it equals is partial derivative of g with respect to x, so that's this function now, minus partial derivative of f with respect to y. So that's what I have for Green's theorem. I even wrote it in green. I don't know if you could tell on the screen. It's too bad. I'm wasting these markers for nothing. I wrote this part in black. But here the formula is in green. And anyways, maybe one more thing to say, and I will change colors for these. What do I mean by positive oriented? I'm talking counterclockwise. Right? Like when you do the unit circle, if it were negative oriented, you'd be going clockwise, and that's not what we usually do in trig. Okay? So piecewise oriented, I mean counterclockwise. Oh, piecewise smooth? We know what smooth means, right? Smooth means no cusps. So piecewise smooth means Green's theorem's going to work even if you have a cusp or 2 or 3 or 100. It's okay. You can make it work in pieces. Kind of like when we do regular integration and we have cusps, a lot of times we'll just split it into 2 integrals. Same idea. Okay? So it's kind of a neat theorem. So I think I better stop and take our break and then come to it after break. I was looking back, we did an example kind of like this when we did the group work. We had different paths from one point to another, and because we had a conservative vector field, remember we got the same answer every time. We got 3 over and over again, right? Okay. So here's the integral I'd like to compute. And I'd like to use our new notation so that you get used to it also. Okay, so here's an example. Let's compute, and I'm just putting the circle here because you're going to see that the path that I'm interested in will be a closed path, okay? And we're going to integrate y squared dx plus 4xy dy. But I guess the most important thing to say now is what is the curve C that I'm talking about? Okay? And so I'm picturing the following. I'm going to graph over here. Let's start with the origin here. Let's start with 0, 0. And what I'm going to do is I'm going to move along our good old friendly parabola that goes through 1, 1, and it goes through 2, 4, right? So this curve here so far is y equals x squared, which I'm very familiar with. But then I'm going to come back to make it a simple closed curve. I'm going to come back along this brown line, which would be that'd be y equals 2x, right? Yeah, because this is 2 comma 4. So you guys understand the curve? I'm saying oriented positive way, so oriented clockwise. We're going to go that way along the green curve, and we're going to come back this way along the brown curve, and then I will be going counterclockwise, that's the positive orientation, around my region R. You guys with me on this? Okay. So I'd like to use Green's theorem. And region R is this region right inside. Green's theorem says this will be the double integral of R over R of something. Okay, so my question is, do you know what to put where?
I'm sorry, can you go back for a second?
Yes.
I'm not following why you chose y equals x squared and y equals 2x based on the problem that was given.
That's part of the problem.
So you just said because I chose it and we're following, and I'm okay with that.
This is the problem.
Oh.
So I have to say where C is the curve
Gotcha.
over there. Where? Right there. You'll see on the homework, they're going to say C is the curve where you follow this and follow that. You know, is this one smooth? Well, it's piecewise smooth. It has 2 cusps. You see them? But the answer is that you can compute this using the line integral method that I showed you. And I'll show you that. That's good practice for us. We still have to do the line integral homework, a lot of us anyways. But Green's theorem is really nice here. We just turn this into a double integral. And you guys just took your test on that, so this is fresh in your mind, right? Oh, but what we need is we need to know what we're going to integrate. So where it says dg dx, I think you'll understand that it would be very natural for me to put 4y, right? Because that's a beautiful function of x and y. And when we take the partial derivative with respect to x, right? So again, g is the function next to the dy. What else am I going to write? I'm going to write minus what? 2y. Yeah? Because that's the partial derivative of f with respect to y, and that's the function next to the dx. Any questions so far? Okay, so we're integrating 2y. Right? Now, what am I about to do? I'm about to turn this into an iterated integral. Do you guys want me to do this dx dy or dy dx? Thank you. I'm glad you said that. I mean, I could do either way, but it's so convenient, right? I mean, we have y by itself. So what should be the bounds of the inner integral? Well, 2x is the upper bound, right? And x squared is the lower bound. I mean, boy, too bad I didn't give you this on the test. Now, how about the limits of integration for dx? Yeah, those are numbers, 0 to 2. Paul, you should have done this. All right, well, maybe. So let's see. We integrate, and we get 0 to 2. Oh, even nicer. When I integrate 2y, it becomes y squared. And we're just going from x squared to 2x. And then we just have to integrate dx after that. My goodness, this is easy. 0 to 2. So that would be 4x squared, right? Minus x to the 4th. Does that look right to you guys? Yeah, I think so. And now when I integrate that, let's see, I get 4/3 x cubed minus 1/5 x to the 5th from 0 to 2. So let's see, 2 cubed is 8, so I get 32 thirds minus, and 2 to the 5th is 32 also. 32 fifths. Wow, that's really cool. So it's 32 negative tooths? Just kidding, that's not what we get. We get, well, the common denominator would be 15. And so 5 times 32 minus 3 times 32, 2 times 32, 64 fifteenths. That was not too bad. Okay. What if we wanted to do the same problem the line integral way? Well, okay. So if you want to do it the line integral way, of course you need to split it up, right? You're going to rewrite in the following way. You would say, hey, the total curve, y squared dx plus 4xy dy, is equal to, well, you would move along curve number 1, right? Curve number 1 is the parabola, right? And of course, we'll do y squared dx plus 4xy dy. And then plus curve number 2, y squared dx plus 4xy dy. Okay, so how much of this should I do? Well, let's do some of it. To do curve number 1, we need to parameterize curve number 1. Can we do that conveniently? Sure. Let's let x equal t, then y equals
T squared.
thank you. Right? Because y is x squared. By the way, I think that this is a really convenient notation I have here. I'm not writing all the r's anymore and the parameters. I'm kind of, they're a little bit behind the scenes here. Everything's in terms of t or in terms of x. Some books will teach it that way. They'll say, hey, your parameter is really x here, because x is t, right? By the way, what is dx? That's the same as dt, right? What is dy? 2t dt. Yep. That's okay? So, oh, I should say one more thing that's very important about this curve. You need to establish what are the limits on t to traverse the curve.
0 to 2.
Yeah, since t is the same as x, we're going from 0 to 2. That's true. Let's try the same game with the brown curve. And then we'll do the calculations. So let's see. For the brown curve, C2, well, okay, so I guess I could say x equals t, y equals 2t. I could say dx equals dt, dy is 2 dt, and then there's one other thing. Oh yeah, what should t go from where to where?
Should still be from 0 to 2.
Well, it's interesting.
From 2 to 0.
I'm going from
Yeah.
2 to 0, right? So I guess I don't want to write it this way. Let's just say from t equals 2 to t equals 0, and we'll see how that plays out then. Okay. So I want to do the computation. Let's do the green part first. Here I go. Let's see. We would integrate from, well, 0 to 2, right? What would we integrate? It says y squared. So I would write, yeah, because it's t squared squared, right? T to the 4th. dt, because that's dx. Plus, and now 4t squared, and dy was, oh, look at this. You actually get a 2t dt showing up, right? So you have to be a little careful here. All of a sudden, my notation is starting to get a little bit sloppy because when I was in Calc 1, I never wrote dt more than once, did I? I'll do it very momentarily.
You just factor it out.
Yeah, and it works perfectly, right? So you get the integral from 0 to 2 of t to the 4th plus, what would this be? 8t to the 4th? Is that right?
Yeah.
And then that's dt. So I'm integrating 9t to the 4th. All right. So when I integrate 9t to the 4th, it becomes 9/5 t to the 5th from 0 to 2. And so that piece, I guess I get 32 times 9. Well, let me just write that. 9 times 32 over 5. Okay, maybe it'll combine nicely with the brown part. We'll see. Now for the brown part, how does this work? So I need to add on integral from what to what? 2 to 0. Is it exactly the same? Not, why not?
Because y is different.
Yeah, we have a different parameterization, right? So now it is 2t that we're squaring. Dx is still dt plus 4t, 2t, and then 2 dt. Oh boy. So I'm guessing, question? Okay, I'm guessing most of you, when you see this 2 and this 0, would you guys do this then? Turn it into a minus from 0 to 2? That's what I usually do. I don't know. I mean, right? We know that f of a minus f of b is the opposite of f of b minus f of a. So it's minus a bunch of stuff integrated dt. What's the bunch of stuff? Let's see. 4t squared. Is it plus 8t squared? 4, 8, 16t squared? So I'm integrating 20t squared? Okay, so I'm going to subtract 20 thirds t cubed as I go from 0 to 2. Now 2 cubed is 8. So that's 9 times 32 over 5, but I'm subtracting 8 times 2 is 160 over 3. And you can work out that that does indeed give me 64 over 15, obviously, right? Well, the denominator's right, right? 15. And I think if you multiply the top by 3 and that by 5, I think you're going to get 64. You could check that for us.
Yeah.
Okay. So yeah, Green's theorem clearly is superior here. But it's also good for you to see how these line integrals work, because some of you are still working quite a bit on that. Let's look at a few pictures from the book. There's a lot of good stuff in here. Okay. Green's theorem. Notice they're going to write it a little bit differently than I will, because they're going to talk about circulation again. Vector field F, negative y, x. This is what I went over at the beginning of class. That's the circulation force field. Okay? And so, hey, there's the picture, right? Let's look at this. This is really cool, I think. To demonstrate what's going on with Green's theorem, they start, drag the symbol to move the point P. Well, I'll try that. Okay, I could put this point anywhere, huh? So I guess the question is, as I move around the curve, how much rotation has happened? Interesting. They say visualize it as a paddle wheel. Anyways, their circulation form of Green's theorem, you'll notice that I didn't list the first component. I I listed the second equality, right, as what I think of as Green's theorem. Honestly, that's kind of easier computations to do than the dot product thing. Okay. Oh, yeah, the two-dimensional curl. I should have mentioned that. Let me put that on your notes. This quantity right here, where? This. This is called the curl. The curl of, well, I guess it would be f and g. Now, this is a 2D version. Usually when people say curl, it's 3 dimensions. Dr. Stitz on Monday, when he substitutes for me, one of the things he's going to be talking about with you guys is what the curl vector is. And it's a 3-dimensional cross product. You don't even have a cross product in 2-dimensional, really. But if you did, this is it. And you'll probably see why that is on Monday also. So that's something that will come back. Anyways, I want to get to the corollary to Green's theorem because it's really cool. Where'd it go? Ah, there it is. Calculating area by Green's theorem. Here it is. The area of a region enclosed by a curve is given by these different expressions. You can take the line integral of x dy, the line integral of y dx, or you can take an average in a sense. Let's write that down, and let's see what's going on. So, corollary. You know, this is basically going backwards from what we just did. Think about what we just did. We just did a double integral to compute a line integral, right? The corollary says, under the conditions of Green's theorem, we can use line integrals to compute area. Which is sometimes easier. It's kind of cool. They teach you this theorem and then you kind of work with it forwards, work with it backwards. Anyways, the theorem would say the following, that area is equal to, so we can either do 1/2, actually, usually we move the 1/2 out front, right? Yeah, I'll do that. 1/2 the line integral, and this would be, say, x dy minus y dx. That's one way to write it. And that's equal to, well, the line integral of just x dy works, and that's also equal to the line integral of, well, it wouldn't be y dx, I need a negative out front, so negative y dx. Okay, I should prove that. Although we didn't prove Green's theorem yet. But this we can prove from Green's theorem pretty quickly. What we're doing here, guys, is we're using good choices of f of xy and g of xy. So we're using Green's theorem and we're doing good choices of f of xy and g of xy. how does this work? Area, we know, of my region R is equal to the double integral over R of 1, right? 1, I'm sorry, dA. So when I say we're doing good choices of f of xy and g of xy, watch this. Suppose that you make f of xy equal to negative y. And suppose you make g of xy equal to 0. Okay. What would Green's theorem tell me? Well, Green's theorem would tell me, let's write the double integral for Green's theorem first. The double integral of what? Remember, Green's theorem. Here, let's write it up above. Yeah. It was d partial of g with respect to x minus what?
Partial of f with respect to y.
Yes, that's what goes in the double integral, right? R. So if I choose this f and this g, you could see that the double integral is going to say what dA? Well, I guess it would be 0, right, for dg dx, minus what? Ah, that's nice, because then what am I integrating? 1. That's why I get area. So if I'm clever about my choices, I can compute area this way. Now, what does the left-hand side of Green's theorem say? It says you have a line integral. Do you remember what it says? Doesn't it say f dx plus g dy? Right? Okay, so what would that be in our example? We have the closed line interval of what? Negative y dx, which is what I said right here. That's one way to get area. Are you with me? If I were to choose f is equal to 0 and g is equal to x, I bet you could figure out what that does. That gives me line integral of x dy.
Does that really prove it, or does it just prove it just for those one cases that you specifically chose?
It proves it for these two cases, and there's only one more case. That's why this is a corollary. We're not proving Green's theorem. We're using Green's theorem to compute area. Some of the homework problems are going to have you do this kind of thing. Okay? Matter of fact, I wonder if I have a good example. Sure, here's a good example. Oh, okay, yeah. So let's do this. Let's find the area bounded by y equals x squared and y equals the square root of x. That could be a nice Calc 1 problem, actually, right? Well, what's it look like? Y equals x squared, of course, is a parabola. Y equals square root of x. Yeah, I mean, where do these things intersect? They intersect at 0, 0 and 1, 1, right? So they both intersect at 0, 0 and 1, 1. And so you have, I guess the region R I'm looking at is right here, right? So I could do this using Calc 1 techniques for sure, but I said let's try to find that area using Green's theorem. How does it work? Okay, well I guess, and maybe this is not the simplest example, but it's not bad. If I'm going to use Green's theorem, I'll do it with line integrals, right? And so maybe the thing to say is, okay, we need to talk about C1 and C2. So let me draw a zoomed in version of this. Here's y equals x squared. That's my curve number 1. And I'm going to go this way around the curve again. And then I'm going to come backwards along C2, right? So that's the game. So let's see, to parameterize C1, what are we going to say? We're going to say x equals t, y equals t squared, and we're going from t equals 0 to t equals 1, and that'll bring me along the curve. Make sense? Now for curve number 2, I have a suggestion. I'm going to suggest that we make x equal to t squared and y equal to t. Is that okay? Because that'll get rid of, no one likes the 1/2 power, right? So we can use this parameterization, and then what should we go from where to where? I guess from 1 to 0? Does that work? Let's see, 1, 1 to 0, 0. Okay. Or another way, what if we did this? Another way of doing C2, we could say x equals t squared, y equals negative t. From almost.
-1.
I guess it would go from -1 to 0, right? That's another way of doing it. So maybe I'll do it this way. Bless you. That's kind of cool. Okay. So now we're going to go ahead and find these line integrals, and then we have it. So let's see. The area would equal, here, let's do this one, since I'm, oh, maybe not. Yeah, I'm pushing time all of a sudden. Hold on a second, let me think and look and decide. So here I go. I mean, we got to finish the example, I think. So closed integral over c of x dy. And again, I'm thinking of this parameterization. This equals the integral from 0 to 1 of, and again, with this parameterization, I guess you could write t times what? 2t dt plus integral, and again, with this parameterization, which is kind of nice to do, -1 to 0 of what? I guess it would be t squared would be x times negative dt, right? So we're integrating from 0 to 1 2t squared dt, and we're going to add to that the integral from -1 to 0, well, maybe we'll subtract the integral from -1 to 0 of t squared dt. All right, so this one is 2/3 t cubed from 0 to 1 minus this would be 1/3 t cubed from -1 to 0. So I get 2/3 minus 0 from the first integral minus 0, and then wouldn't it be minus, oh, minus -1/3, right? No,
Throw that in brackets from 0 to 1.
yes. So it's minus minus minus, which is minus. 2/3 minus 1/3 is 1/3. That's the area. Yeah. I knew it's not 1, because 1's the area of this square. So 1/3 of the area is between those two curves. That's kind of cool. You didn't know you could split up a sandwich that way, right? Get out your parabolic cutting board. All right, kind of cool. Learned something new today. All right, so to finish, I said at the beginning of class, after we did our little quiz, I tried to sum up some of the ideas of section 16.3, all about F being conservative. Now this weekend, how many people plan on getting caught up on calc homework? Let me ask that. That's outstanding. I'll get caught up on grading take-home exams. So we'll have a lot of fun next time I see you guys. Wednesday, right. So F is conservative. If you have your homework done Monday, by the way, Stitz would love to take those questions, because I'm not going to give him enough to do. I can just see it. Because he goes fast. You will not, I mean, he'll slow down, but it'll be a different level. The man knows what he's doing. All right, so F is conservative, right? I told you guys there's a test to see if F is conservative, and you kind of stared at me like, huh? So what's the test? The test is you want to look at this. df dy minus dg dx. I feel like we just saw that. Wait a minute. Where was that? Well, in Green's theorem, we had dg dx minus df dy. I have df dy minus dg dx. Well, is that the same?
Not negative.
It's just the opposite. That's the opposite of the curl, right? So if this is 0, right? If the curl is 0, actually it wasn't just if. It was if and only if F is conservative, right? So what I want to do is give you some idea why that's true. Why would it be true that this is 0 if and only if F is conservative and vice versa? That I might be able to show you. Okay, so here we go. One direction. Suppose F is conservative on the region R. What does that mean? Then there exists some function. What am I going to write, guys? Phi of xy such that, what would I say? I would say the gradient of phi, what does that mean? It means we're tired and out of time, Paul. Doesn't it mean we get a vector of partial derivatives? Partial of phi with respect to x, comma, partial of phi with respect to y, right? Now, if that equals f, F, by the way, we've been writing this way in the two-dimensional case, right? So that's what I have. Yeah? Okay. Yeah, I guess I'll come back to it. 11:50. Not going to hold you after for this. All right, we'll come back to it. Nice work today, guys.